all work itself out by the end.
Good job, Noah.
All right, so
Did your best.
the 310 will be the last lesson in test 3. The textbook does such an overboard job of showing what's a fairly simple idea that I'm gonna speak very little about what's actually going on here. Is that okay? I wanna give it to you in a way that the AP is gonna expect you to deal with it, and in all practicality is doing the same thing that the textbook is doing without an alphabet soup of notation. Okay? So 310 is about linear approximations. A linear approximation is just a tangent line. That's it. That's all it is. You might as well call it a tangent line approximation. So if I want to make a linear approximation to a curve at a specific point, I'm just going to find the tangent line to the curve at that point, and then plug in whatever value of x they want me to find the approximate y for. That's it. That's the entire idea for 310. Now the textbook presents it in like a really kind of over-the-top way, which is fine, but that is the idea. That's all we're talking about doing. So oh, come on, you stupid thing. All right, we're just gonna be difficult, fine. So this is the kind of way the text or that the AP would present asking you to make a linear approximation. So this is kind of the verbiage they would use. This is the kind of setup they might use. So it says a differentiable function f has the property that f of 5 is equal to 3 and f prime of 5 is equal to 4. What is the estimate for f of 4.8 using the local linear approximation for f at x equals 5? It's given us a point, 5, 3, and a slope, 4. Yeah. Can we just not? Yes.
Can I use the bathroom?
Sure. Everybody okay? So that's my tangent line for my linear approximation. If I want to find the linear approximation at 4.8, well, f of 4.8 is approximately that linear approximation, which is going to be 4 times 4.8 minus 5 plus 3. 4.8 minus 5 is negative 0.2, times 4 is negative 0.8, plus 3 is 2.2. What did I really do here? I wrote the tangent of the equation for the tangent line of the curve, and then plugged the value for x. Whenever you hear linear approximation on AP, that's all you're going to be doing. Just write the tangent line at the specified point, and then plug, the other x value that you're looking to approximate into the tangent line, and move on to the next problem, because you're done. There's nothing more to it than that. Does that feel okay? That's the kind of thing that would appear on your test 3. Question be phrased similar to this. That's the way it'll appear on an AP exam. Now, they could ask, if you're given more information, what the error is between your estimate and the actual value. You need more information that's provided in this problem, because you actually need to know what the y value for 4.8 is. But if you just look at the difference between your approximation and the actual y value, that's like your error. That's all we're talking about. If you guys took AP Stat, anybody in AP Stat or taken it before?
I'm in your IBSO class.
Oh yeah. When you talk about residuals, when you do like a linear approximation or a linear regression line, you talk about the residual, the difference between the approximate value from the linear regression equation and the actual value. It's the same idea here. Does that make sense, Anthony? I think you're the one person that said I'm in AP Stats right now. You guys talked about residuals already?
I took it last year.
Oh, you took it last year, so you definitely talked about it last year. Perfect. Feel okay? But that's the idea. That's like all 3 tennis boils down to writing equation for tangent lines and then using them to make an approximation. What can you say? What should you be able to say about your tangent line approximation? In this case, we made it at the point x equals 5. As I get further away from 5, is my approximation gonna get better or worse? Worse. That's it. It's the only thing I had to say. That's the only other thing I have to say. Everybody intuitively was able to guess that, which is great. That's it. That's the whole idea for 310. Cool? So we got what, like 15, 20 minutes? You guys just want to buzz through some of these test questions here, or the multiple choice questions that we kind of listed? Okay. Who can do 2 with no calculator? Maybe even in your head. Who's got it?
To see.
Not C. So many of you guys are writing this out by hand.
It's 32.
It's not negative 32.
It's not an option.
It is an option. It's B.
How is it not? Oh, I can't see.
Wait,
It's how?
can you?
It is A.
You're still doing it all the time.
And then when you plug 1 in, you get 4 times negative 8 times 2. Yes, sir?
I'm having problems syncing my tablet. Can I go to an IT? Is that okay? Thank you.
What's the chain rule?
It's a chain rule, bro. Yeah, that's right.
Oh, X to the 4.
You see it? How about 3? Yeah, it's quotient inside of a chain rule, but that's not how I would do it. What would I do? I'd use logarithmic differentiation to do this. 100%. And right away, without even having to fully simplify, I'm down the first three options, because none of them are going to have the common denominator of x plus 1 to the 6th. Everybody okay there? Now I just have to make a decision here. Which one is it going to be? Well, to make that common denominator, I have to do this, right? Oh my gosh, guys. Mr. Kulik, you're so dumb. Where am I dumb at? Where am I dumb? What'd I do dumb? Who sees it? Because it's not any of them, right?
That's why I was so confused.
Come on, you need to speak up. If you see it.
Well, I didn't know if it was. Yeah, I thought you knew better than I did. So it's.
Oh my God. There we go. Now what's that? No? You see it or no?
I'm not drawing the connection.
All right, that means that. Could have started with that also and not done logarithmic differentiation. That ices, instead of having the quotient side of the chain, now you have the chain inside of the quotient, which is probably just a little bit easier to deal with.
So if you started with x to the 5th over x plus 1 to the 5th, you could have just done the quotient rule?
There's still a chain inside of it for the x plus 1 to the 5th.
Yeah.
But that's probably an easier order than chain with the quotient inside of it. Is the quotient with the chain inside of it is probably a little easier to handle, my opinion. But yeah, you could, any way of going about that. I thought the simplification would come along a little bit easier when I did the logarithmic differentiation. I was disappointed that it didn't work out as neatly as I thought it was going to. When I first looked at it, I'm like, that looks like an excellent candidate for that, and it didn't work out to be as easy as I hoped it was going to. I was expecting when I multiplied the x back over, like a whole bunch of stuff to cancel in it to be really obvious. F and g are twice differentiable functions such that g of x is equal to e to the f of x. And g double prime of x is equal to h of x times e to the f of x. Then h of x is equal to what? Oh boy, guys, this looks rough, right?
Yeah.
Where do we start? What do I start by doing?
They're inverses.
No, there's no inverses here. I know. Yeah, that's right, Ava. So we need to know about the second derivative. We better start just by taking the first derivative. How do I do the derivative of e to the f of x?
Isn't it just f of x?
Nope. Times the derivative of f of x. Right, because it's a chain rule. You guys see it?
Yes.
Okay. Lucy, are you good?
Yeah.
You're making a face like
Just continue.
Okay, it's okay. I'm just checking. Now we'll do the second derivative. How do I take the derivative of e to the fx times f prime of x?
That's a product rule.
To do I need to do a product rule here, yep, and there'll be a chain inside of it.
And that's the natural log one, right?
Well, there's no natural logs here.
But whenever you're taking the derivative of an exponent, isn't it like?
Well, the e to the x is not a big deal
Okay.
because it's going to be the natural log of e, so that's nothing.
The natural log of E0 or?
1.
Okay.
Everybody okay with what I've written here? Ugh. There we go. So far, so good? Okay. The derivative of f prime of x is? Very good, Frankie. F double prime of x. And the derivative of e to the fx is? Mm-hmm. Because we already did that. What's f prime of x times f prime of x? Going to just be f prime of x squared. Everybody agree? F prime of x times f prime of x should just be f prime of x squared.
Mm-hmm.
Now I have to get it into this form, so I need something times e to the fx. Notice I have e to the fx in each term. So if I factor that out like a greatest common factor, and that one. Well, that's a really good test of how how comfortable you are with notation, product rule, chain rule. Really kind of make sure that you understand what's going on there symbolically and you can really push those symbols. Right? That's not trivial by any means. Everybody okay? All right. Ready to do 5? Notice next to the number 5 has that little red symbol there. What's that symbol look like? Calculator. That just means that this question would have been a calculator active question from an AP exam. I don't know what you would have used your calculator to do for that problem, because I would have done the whole thing. I would do the whole thing by hand for number 5, but that's what that symbol means, is that it's a problem from a calculator active portion of an exam. Here we're looking for the derivative of e to the tan squared x. What do we need to do that? How many chain rules do we see here?
2.
2. Yeah, very good. So f prime is going to be the derivative of the outside, which is nothing, times the derivative of the inside. And remember that like tan squared really means this, right? The derivative of tan squared is a chain rule. The derivative of the outside is going to be
X squared.
yeah, so 2 tan x times the derivative of the inside. And what's the derivative of tangent? secant squared x. So like, that's our answer. So again, as soon as I see that 2, all 3 of those boys are gone. I could look at this and eliminate it down to 50-50 because I'm like, where's my 2? Should be there somewhere. That's our guy. Oh, I love this one. If f of x is equal to x squared plus 2x, then the derivative of f of the natural log of x is equal to, how do I do this? What's that? You can, I wouldn't do that first though. Yeah, so I would treat this like a chain rule, right? Do you agree? And what's the derivative of f of x? So you're going to have 2 natural log x plus 2 all over x. Way easier than, Mark, what you're describing would work. It's going to be a lot messier than what we did here though, right? Because you have all those chain rules now to deal with where you have like log of x squared. So again, it'll work. What you described will get you the right answer. I think that's a little cleaner. But this is good. This is part of what I want to have happen here is you guys to suggest stuff and me to go, okay, that'll work. This way is probably a little bit quicker and to see what that looks like. Because sometimes it's about the sequencing of doing the problem, like me waiting to put the natural log in until the very end simplifies that problem immensely. Brooks.
So are you taking a derivative of something to the power of something, so like e times e to the power of 5x minus 2, it's the original thing, so it'd be the exact same thing, was times the natural log of the exponent, correct?
No.
Or the base?
Yeah, the base.
Okay.
That's the rule you're asking.
That's the same thing for the chain rule, but it's just being applied to the next one.
Now it's a chain rule. Should we do this? How do we do 7? It's a chain rule, right? How do I do the derivative of 2 over x? Oh, it works, but that's so much overkill. Why not just think about it as 2x to the negative 1, right? Then we can do it in our head.
Good afternoon, Notre Dame Prep. As we come to the end of the school day, I ask you to please pause for a moment to reflect on our day. Dear God, help us look at the example of the saints who have gone before us. May we reflect on their faith and be inspired by their courage and determination. When we feel weak, help us gain the strength we need from the example of the saints so that we can respond to your call. Amen. Teachers, you may dismiss your students as you are ready. Have a wonderful day, Notre Dame Prep, and God bless.
See you later, guys.
Thank you, Dr. Phillips.
Have a good day.
Thank you.
You're welcome. You're welcome.